The objective of this presentation is to gain insights into the diffusion of gas molecules such as hydrogen, argon, methane, carbon dioxide, propane, butane inside one-dimensional mesoporous channels. Let's first have a look at the IUPAC classification of pore sizes. Three classes of pore sizes are distinguished. A micropore has pore diameters less than 2 nanometers. A mesopore has pore diameters in the range of 2 nanometers to 50 nanometers, and a macropore has diameters larger than 50 nanometers. The focus of this presentation is on mesopores. In order to understand this classification, let us consider the energy of interaction of gas molecules with the pore wall, plotted as a function of distance from the pore wall. Very close to the pore wall, we have repulsive forces, and then followed by attractive forces in this beyond a certain distance from the pore wall. For hydrogen, the energy of interaction with the pore wall reduces to zero at a distance of 1 nanometer from the pore wall. The same is true for argon, drawn here in blue, and for methane, drawn here in red. In all cases, the energies of interaction are large for distances smaller than 1 nanometer from the pore wall. For distances larger than 1 nanometer from the pore wall, the energies of interactions are zero. In other words, if we have a 4 nanometer silica pore, there will be a region near the pore wall where the molecule wall interaction energies are of significant importance. And there will also be a central core region where molecule wall interactions are of negligible importance, and the motion of molecules is dictated by molecule collisions. Therefore, the description of diffusion inside mesopores requires us to determine the contributions of molecule wall collisions to the diffusivity, and also the contributions of molecule collisions to the diffusivity inside the pores. Let's have a qualitative feel for this. We look at animations of the motion of hydrogen molecules inside a 4 nanometer silica mesopore, and we note molecule wall collisions taking place as well as molecule collisions in the central core region. For methane, there appears to be a larger concentration of molecules near the pore wall because the interaction energies with the pore walls are more significant, and methane is more strongly adsorbed and appears to have a higher concentration near the pore wall and a lower concentration of methane molecules in the central core region. In order to determine the diffusivities of these two gas molecules, we need to combine molecular wall collisions with the molecule collisions to determine the diffusivities of any gas inside a mesopore. In the literature, the formula for such a combination has been derived by Bosanquet, where the self-diffusivity of any gas molecule inside a mesopore is considered to be a sum of the resistance due to the molecule wall collisions and the resistance due to molecule collisions. And The molecule wall collisions are described by the Knudsen formula, and the molecule-molecule collisions are described by the kinetic gas theory. In this presentation, we test the applicability of the Knudsen and Bosanquet prescriptions by use of molecular dynamic simulations for 2 nanometer silica pore and a 3.4 nanometer covalent organic framework. The molecular dynamic simulation data and the background theory are provided in the publications that are listed on the slide. Let's look at the diffusivities inside a 2 nanometer silica pore, for which molecule wall collisions are of dominant importance and molecule-molecule collisions are of negligible importance. And we consider 3 guests, hydrogen, argon, and methane. In each case, we have a total loading of 6 guest molecules, and we track the trajectory followed by one of the guest molecules as it collides with the wall. This is for hydrogen, and we see that the hydrogen molecules collide with a rough silica surface and experience a random trajectory, and the angle of incidence when a molecule of hydrogen strikes the wall bears no relation to the angle at which it gets reflected from the pore walls. Here we look at argon, which is more strongly adsorbed than hydrogen, and we note some differences with the trajectory followed by hydrogen, in that argon has a tendency to stay closer to the surface and occasionally gets reflected from the pore wall and enters the central region. Here we follow the trajectories of methane molecules. Methane is more strongly adsorbed than argon, and we would expect the trajectory of methane to remain closer to the pore wall than argon and hydrogen. We'll also note that the methane molecule when it strikes the wall, has a tendency to remain closer to the wall, and only later does it get reflected from the wall and enters the central region. Now, in each of these cases, we can determine the diffusivity from molecular dynamic simulations and compare those MD data with the data calculated from the Knudsen formula. Let's have a look at the Knudsen formula. And this formula was derived by Martin Hans Christian Knudsen. The Knudsen diffusivity formula is depends on the pore diameter, the temperature, and the molar mass. R is the gas constant. And in deriving this formula, it is assumed that the molecule suffers diffuse reflectance. In other words, the angle of incidence bears no relation to the angle of reflectance. This is true for a practically non-adsorbing molecules such as helium. It is also true to a certain extent for hydrogen. A strongly adsorbed molecule such as CO2 will experience a situation that is somewhat different. As it strikes the wall, there will be a tendency to hop to a neighboring adsorption site before returning to the core region. We now compare the MD data for the diffusivity, denoted by this di with 0. We determine the diffusivity for a variety of loadings and extrapolate that to 0 loading to compare with the Knudsen formula. And this graph plots the ratio of the MD data for the diffusivity at 0 loading to the diffusivity calculated by the Knudsen formula, plotted as a function of the Henry coefficient, which is a measure of the adsorption strength for a variety of guest molecules such as argon, krypton, methane, ethane, propane, normal butane, cyclohexane, normal pentane, normal hexane, and normal heptane. And we note as the adsorption strength increases, the larger is the deviation from the Knudsen formula. And for, say, butane, the diffusivity determined from MD is only 10% of the value determined from the Knudsen formula. Put very simply, sticky molecules have low mobility, and smaller molecules with poor adsorption strength appear to follow the Knudsen formula more accurately. Another way to establish the importance of adsorption on the mobility of molecules is to determine the diffusivities at various temperatures. With increasing temperature, the adsorption strength decreases, and therefore we should expect the diffusivity to be in closer agreement with the Knudsen formula. This is indeed found to be the case for methane in 2 nanometer pore, indicated by these circles, and a 3 nanometer pore indicated by these squares. In each case, as the temperature is increased, the ratio of the diffusivity determined from MD to the value of the Knudsen prescription approaches unity. Conversely, as the temperature is reduced beyond the room temperature, which is about here, the adsorption strength increases and the deviation from the Knudsen formula is even larger. Now let's have a look at pores which are larger than 2 nanometers, for which both molecule wall collisions and molecule-molecule collisions are important. In this case, we perform MD simulations for a 3.4 nanometer covalent organic framework called BTP-COF. It has one-dimensional channels that are hexagonal in shape. This table provides some data on the crystalline structure. This gives you the dimensions of a unit cell. This is the framework density and the pore volume. Let's look at 4 molecules with increasing strength: hydrogen, argon, methane, and carbon dioxide, and see how these molecules traverse the pore. Hydrogen, as you might expect, since it's poorly adsorbed, doesn't remain on the surface and gets reflected and returns to the core region. Argon, which is most strongly adsorbed, has a tendency to remain on the surface and hop to a neighboring site before returning to the core region. And in the core region, it experiences molecule collisions. For methane, that has a higher adsorption strength than argon, there is a higher concentration of methane near the pore walls and a lower concentration of molecules in the core region as compared to argon. For carbon dioxide, most of the molecules are close to the surface and suffer a biased motion, and the bias being in favor of motion along the surface rather than colliding with the wall and returning to the core region. You see only a very small fraction of molecules have entered the core region and experiencing molecule-molecule collisions. So for these 4 guest molecules, let's compare the predictions of the Bosanquet formula that combines molecule wall collisions with molecule-molecule collisions. The Bosanquet formula is indicated by these crosses for hydrogen, argon, methane, and carbon dioxide. The Bosanquet formula is compared with the MD simulations shown by these red circles. For hydrogen, the agreement between the MD simulations and the Bosanquet formula is very good. And the agreement is significantly poorer for argon, but as the pore concentration increases, The x-axis plots the pore concentration in units of kilomoles of guest molecule per cubic meter of pore volume. As the pore concentration increases, the molecule collisions become of increasing importance, and since in the molecule collisions are very well described by the kinetic gas theory, the agreement between MD simulations and the Bosanquet formula is very good for high concentrations, say beyond 10 kilomoles per cubic meter, and is poor at low concentrations because at these low concentrations the molecule wall collisions are important, and for argon, which has a finite adsorption strength, the Knudsen contribution to the Bosanquet formula is of insufficient accuracy. The story is identical to that of methane, where the agreement is poorer for low pore concentrations and becomes increasingly good. The Bosanquet formula becomes increasingly accurate as the pore concentration increases to say beyond 10 kilomoles per cubic meter. The accuracy of the Bosanquet formula for CO2 is significantly poorer than for methane because of the much stronger adsorption strength of CO2. Let's have a look at three other gas molecules. This is ethane. None of the ethane molecules appear to have entered the central core region. This is propane. Most molecules are concentrated near the pore walls, and molecule wall collisions are of much greater significance than molecule collisions, except for this molecule here, but it doesn't have any other molecule to collide with. This is normal butane that hops and moves along the surface rather than colliding with the wall and returning to the central core region. In all these three cases, the agreement of the Bosanquet formula with the MD simulated data is extremely poor. Let's have a look at hydrogen CO2 mixtures. With the hydrogen molecules shown by these white spheres are almost uniformly distributed, whereas carbon dioxide is concentrated near the pore wall, and therefore to calculate the diffusivity of these molecules in the mixture, one needs to take account of the segregated nature of the distribution of molecules. The strongly adsorbed molecule concentrates near the pore wall. The poorly adsorbed molecule is more uniformly distributed. The same is the story for hydrogen methane mixtures. I think the message that has been obtained from these MD simulations is that the higher the adsorption strength, the higher is the concentration of any gas molecule near the pore wall, and the Knudsen formula for molecule wall collisions becomes increasingly inaccurate for molecules that have a high adsorption strengths.